Good afternoon, everyone. This is Ria Pahuja from the Economic Times. We are here for another webinar on multiphysics simulation for vehicle electrification. As the Indian automotive industry gears up for the impending electrification revolution, it is crucial for vehicle manufacturers to look for new and inventive solutions to deliver fuel-efficient and clean vehicles in a faster and more cost-effective way. A multiphysics simulation software enables you to create high-fidelity models of different aspects of electric vehicles, such as thermal management, drive cycle analysis, capacity fade and aging, and thermal runaway in battery. The prediction and mitigation of electric motor noise, cooling of onboard electronic components, and design consideration for electric powertrain can also be supported. During this webinar, we'll discuss how COMSOL Multiphysics software can facilitate the design and analysis of critical components within the electric vehicles. This webinar will also have a live demo of the software. So for this webinar, we have today with us Mr. Vineet. Mr. Vineet is the Managing Director of the COMSOL Multiphysics Private Limited. He has served in this role since 2009 and his primary responsibility is to oversee the Indian operation of COMSOL. He also has and holds a PhD in mechanical engineering. I now hand over this webinar to you. Mr. Vineet, please take over.
Thank you. Good afternoon, everyone. Today we are going to talk about multiphysics simulations for vehicle electrification. The brief agenda for today would be, I would start with an introduction to COMSOL Multiphysics. I'm not sure how many of you are familiar with our software, so I'll give you a brief introduction to the software. I'll follow that up with case studies, some cases that are customers have some problems that our customers have solved using COMSOL. Then I'll also talk about the simulation strategies available in COMSOL, and I'll follow that up with a demo of the software itself. So I'll show you how you can set up complex real-life problems in the easy-to-use graphical user interface that we have, and that will be followed by a question-answer session. So to begin with, for those of you who may be unfamiliar with COMSOL Multiphysics, it's a truly multiphysics software in that you can couple any physical phenomenon with any other physical phenomenon in COMSOL. So irrespective of what physics you're talking about, when you want to capture a real life problem on a computer or in a simulation, normally you have multiple physical phenomena which are simultaneously governing that physical problem. And in COMSOL, you have the flexibility to couple any physical phenomena with any other physical phenomenon. So for instance, if you want to couple structural mechanics with, let's say, electromagnetics and heat transfer, in the same interface, you can couple all of these phenomena in COMSOL, and the list goes on and on. So the same with fluids and structures, or chemical species transport and CFD and heat transfer. All of these can be coupled in a single interface. COMSOL gives you a user interface which is easy to use and where you can couple all of these phenomena simultaneously to capture your real life problem accurately. So whatever you do in COMSOL, our emphasis is on making sure that you always get accurate solutions. Irrespective of how many physics you are coupling, you can be rest assured that in the background, the software ensures that all of these physics are solved simultaneously, and therefore you always get accurate solutions to your real life problems. And to aid this, we have a product suite. So you can see that we have a host of different modules for different physics areas. But like I said earlier, all of these are in a single graphical user interface, which is the COMSOL Multiphysics graphical user interface. I won't talk about the product suite, the modules that we have, because we have over 40 modules. But as you can see here, for different aspects of physical modeling, be it electromagnetics or CFD, heat transfer, structural mechanics, chemical engineering, we have a range of different physics-based modules. Apart from that, we also have some application-based modules, such as the batteries and fuel cells module, the corrosion module, all of which I'll be talking about in more detail later on. And then we also have some multi-purpose modules where, apart from doing your analysis, you can also optimize your problems. So we have some optimization tools and tools where you can link our software with other softwares like MATLAB, Excel, and where you can have a live link with CAD softwares. So all of this is our product suite. Then we also have something called the COMSOL server and the COMSOL compiler, but that's something I'll talk about later on during the presentation. For now, let me start by sharing with you some case studies of some problems that our customers have solved using COMSOL. I'm going to focus, like I said earlier, on electric vehicle modeling. And one of the most important aspects of an electric vehicle, of course, is the batteries, the battery pack. And the individual component of the battery pack, of course, is the battery cell. And as I said in the previous slide, we are a truly multi-physics software, and this is one of our strengths. You can couple complex multi-physics problems and solve them accurately in COMSOL. And the battery problem is as multi-physics as it can get, because if you look at how a battery works, you have mass transport in a battery, but you also have ion transport. So there itself you have a coupling between mass and ion transport, and these reactions are always exothermic. So whenever you have a reaction at the electrolyte electrode interface, it generates heat. And of course the reaction rate is temperature dependent. So as the heat is generated, the reaction rate usually reduces. So here itself you can see it's a complex multi-physics problem. And then of course everybody would like to maintain their batteries at a certain temperature. So you have the thermal problem, which is coupled to this electrochemical problem. So if you want to capture a battery accurately, there are several physics which need to be solved for simultaneously, and COMSOL provides you with a easy to use interface where you can do that. This is a case study from the Institute of Power Sources at Tianjin in China, and they work both with battery packs as well as with individual cells. And in this particular project, they wanted to check for battery safety, and cell safety, as a matter of fact. So they wanted to analyze cell safety and simulate the behavior of cells at various operating conditions. So they used COMSOL, like I mentioned earlier, for a full electrochemical analysis coupled with heat transfer and fluid flow. And using COMSOL, they were able to, for their new cell designs, they were able to identify conditions which led to thermal runaway. Now, earlier they used to do extensive experimentation, and what they noted is that each of the experiments used to cost them 300 USD, and they had to perform hundreds of experiments. Not just that, but each experiment took 1 week to set up and then 1 more week to get results. But once they started doing this accurate multiphysics simulation of the electrochemical and the thermal problem, they were able to reduce this from over 100 to less than 10 experiments per new cell configuration that they were trying out, which led to significant time saving as well as cost saving. Earlier in the previous slide, I talked about a cell level analysis which was done by a battery manufacturer. This is an example from Fiat. Of course, Fiat doesn't make its own cells, but they do source cells and they combine up to 100 cells into different battery packs, which give them up to 350 volts, which is what their EV requirements are. And these cells are wired in series. And because they are wired in series, even if one cell fails, it can impact the entire pack performance. So they have a lot of design constraints. One of them is that the maximum temperature differential between the cells should be less than 5 degrees centigrade. If the temperature is too low, then it limits the amount of charge you can extract from the battery. It also leads to other performance issues in the battery, which we will talk about later on. If the temperature is too high, it leads to thermal runaway, which means you could have electrolyte emission, smoke in the battery pack, or in the worst case scenario, even a fire. And therefore, to meet these design specifications, Fiat used COMSOL to run simulations at different discharge rates Once again, they started with an electrochemical analysis, followed by CFD and a heat transfer analysis at the entire battery pack level. So they wanted to design the frame of the battery as well as the spacing between the batteries, individual cells in the battery pack. And using the optimization tools available in COMSOL, along with the multiphysics analysis, they were able to reduce the physical channels between the cells. So they reduced not only the space, but also the weight of the entire battery pack. And they also realized that they could use a less powerful fan than they were currently using. And they were able to reduce their design time by 70% using these simulations. So these are a couple of examples of battery simulations that I wanted to share with you. I'll talk about battery simulations in more detail later on, obviously, because like I said earlier, this is one of the most important components of an electric vehicle, and also perhaps one of the least known components, so to speak. But apart from battery modeling, you can also do structural, electromagnetic, CFD, and heat transfer modeling in COMSOL. So in the context of, once again, electric vehicles, let me share some other case studies with you. So here's an example of an NVH analysis of an induction motor, and this has again been performed using COMSOL. So just like with the previous analyses, this is a completely multiphysics analysis. You first start with modeling the electromagnetic problem. So because of the eccentricities in the rotor, between the rotor and the stator, you have some electromagnetic forces which cause a vibration in the entire motor. So what we are doing here is starting with the electromagnetic problem and then also solving the multi-body dynamics and the structural mechanics problems. The stiffness in the bushings is also accounted for here, and you can see the forces in the bearings on the one of the top figures over here as a function of time. Mind you, like I said earlier, it's a fully coupled problem. So the speed which is computed from the MBD problem or the multi-body dynamics problem is transferred back to the electromagnetic problem, and it's used to calculate the forces generated, the electromagnetic forces generated in real time, and therefore you can accurately capture the vibrations due to the electromagnetic as well as the structural problem. Now, mind you, all of these problems become even more important in electric vehicles because you don't have engine noise any longer. So all of these sounds, the NVH problems associated with motors, become important. Capturing them accurately, let me rephrase that, become important in an electric motor scenario, electric vehicle scenario. So here's an example of a multi-speed transmission modeled using COMSOL. Now you may not have a multi-speed transmission in an EV, but at the very least, you have a fixed ratio reduction gear, which connects the rotor shaft to the gear, to the wheels. And once again, like I said earlier, noises generated from the gear as well as the motor become very important for electric vehicles since there is no engine noise. So in this particular model, which of course is a multi-speed transmission, you can see that we have modeled a complete structural problem and coupled it with an acoustic problem. So we want to analyze the vibrations and the noise generated in the housing due to the motion of the gears, and that is what is being done here. The vibrations are due to, apart from the vibrations of the housing, they are also due to the mesh stiffness. So COMSOL has built-in tools where you can evaluate the mesh stiffness and transfer it to the multi-body dynamics problem. And once this is accurately captured, the software can also identify the number of teeth in contact, the backlash in the teeth, all of which impacts both the bending in the rotor as well as the noise generated. So all of this is captured here. And then finally, you can see that the acoustics problem has been coupled to the structural problem. So you can see the acoustic pressure field around the gearbox being simulated in this particular problem. So this is another example where you can capture multi-body dynamics problems in COMSOLs. You can couple structural mechanics with electromagnetics. We talked about induction motors earlier. This is an example of a permanent magnet motor, or a PMM, which are used in hybrid and electric vehicles. And of course, these heat up very quickly because they are prone to high eddy current losses. Now here again, you can use COMSOL amongst other things to optimally design the laminations in the core, because this is how you can control the heat losses. Amongst others, we have several features where thin shells can be modeled efficiently, and you can accurately perform coupled thermal, electric, and structural analyses on layered shells. In this case, laminates, but you can also perform composite analysis and couple that with heat transfer analysis and electrical analysis in composites in COMSOL. You can model these problems very efficiently and fast, because you don't have to model the thin domains such as composites or these insulations as a 3D domain. You can model them as shells and still get equally accurate results. Heat generation and cooling of a motor can also be captured using the techniques that are shown over here. Do we take questions now, or it's at the end of the session? I guess it's at the end of the session. Okay. So let me move on to the final case study before I start talking about the software itself and show you how the software looks. So this is an example from a company called Faraday Futures. And this is a case study from the motor group, who've shared a story where they design motors for a generic set of vehicles for a variable platform architecture. Now, this allows for a modular design of an electric powertrain. So they provide a consultancy to EV manufacturers or OEMs. To enable a modular design of the electric powertrain, they need to add or remove motors, adjust battery quantities in the battery packs and the module level, and which helps them collapse or increase the chassis size, depending on the requirements of the OEMs. And therefore, they need to capture both the thermal and structural behavior of the motors along with the electromagnetic behavior. So earlier, it used to take them several weeks to coordinate between the CFD and the structural teams within their company to get the final design of the motors. But using COMSOL, they were able to couple all of these three analyses and solve them simultaneously. And therefore, they were able to significantly reduce the amount of time it took them to design these different motor configurations. The images that you see here, the figures that you see here, are an EI core actuator which was designed using COMSOL. All of these are case studies which are available on our website. So if any of you are interested in more details of these case studies, I encourage you to go to our website and download these case studies. So as you can see, I've shown you examples where using COMSOL, our users or we have coupled different physical phenomena to accurately capture different real life problems. And like I said at the very beginning, this is what we emphasize. The fact that you can always rely on accurate solutions when you capture your problems using COMSOL. So it doesn't matter which physical phenomena you choose to couple. COMSOL in the background will always ensure that all of these different physics are coupled, solved for simultaneously, and thereby give you accurate results. As a user, you will have the flexibility to choose what physics you would like to couple. So you can couple any physics with any other physics in COMSOL. There is no limitation on the kind of couplings that a user can choose to perform in COMSOL. This is something that you will also see when I show you the user interface later on during this presentation. But before I come to that, let me go back to batteries like I mentioned earlier. And the reason for that is, of course, since we have had a batteries module for a long time now, and we have a lot of customers using our software for battery simulations, a lot of people approach us with questions about battery simulations. And one common question is that we don't make batteries, so why do we need to do electrochemical simulations of batteries? We are not battery manufacturers. And I think that's a very important question to address. And therefore, I will briefly talk about the importance of simulating batteries. Now, not just batteries, but in any product development process, it usually comprises of three stages: conception and understanding, design and optimization, and testing and verification. Now, as with any other product development process, so with the battery process, understanding the system is the first step in the development process. And once this is achieved, you can then make predictions on the battery behavior or the battery performance, which are outside the range of your experience, and then innovations come naturally. Why this is relevant for battery users will be evident in the coming slides. So once a prototype is designed, based on such innovations, simulation serves as tools to optimize and control the device for the range of operation of interest. So just to give you an example, with the help of modeling, you can investigate how the variability of material properties can affect the performance of your batteries. Similarly, we can also have quantitative information on certain parameters of interest where it could be impractical to, or maybe even impossible to place experimental probes. Let me give you some more details on what I'm talking about in the coming slide. So in electric or hybrid vehicles, the monitoring unit of the battery is critical for the battery management system, or the BMS. Now, most usually you would like to see the voltage, the temperature, and also the state of charge, or the SOC, and the control of the battery. During battery operation, charge discharge scenarios and drive cycles are involved. And on this slide, in the first two plots over here, you can see the voltage profiles for different C rates ranging from 0.1 C, as you can see, to 4 C, and then a drive cycle, which is the performance of the car. The advantage of performing simulations is that you can monitor several other quantities which would otherwise be difficult to measure. So as an example, you can see quantities such as the internal resistance or the polarization of each of the components of the battery cell, a more accurate cell SOC, or even the SOC of each electrode material can be captured using simulations. These are things that you cannot do with experiments. Why this is important becomes obvious in this slide, for instance. So if you want to accurately capture capacity fade or the performance of your battery with time, it's important to capture the side reactions and the degradation processes, because these lead to several undesirable effects in lithium-ion batteries. Typically, aging occurs due to multiple complex phenomena and reactions that occur simultaneously at different places in the battery, and also due to different operating conditions of the battery, such as the voltage limits, the temperature, and so on. Now, here, this is where I would like to point out that operating conditions play a significant role in battery performance. The same battery pack which performs well, let us say in Europe, may not be able to survive in operating temperatures of 50 degrees centigrade, or high relative humidity environments which it may encounter in India. And therefore, it is important, even if you do not manufacture battery cells and you're a user of battery packs, to ensure that the pack and the cell level degradation is captured accurately for your operating conditions, which your battery manufacturer may not be able to provide you with. Now, this can be done very easily using high fidelity simulations, and that can help you provide clear specs to your battery manufacturer. These phenomena cause not only degradation of performance, which we see in this slide, but it can also lead to catastrophic failure in your battery packs, as we'll see in this slide. So battery misuse can be caused by several reasons. Some of the phenomena have been listed here, as you can see. Note that internal short circuits can occur not just in accident scenarios due to compressive shocks, but also due to lithium dendrite formation, which we saw earlier. And therefore, to capture this, to identify if you will have catastrophic failure, you need to do a cell level analysis of your batteries. So simulation will help you in accurately capturing pack performance And again, like I said, providing better specifications to the manufacturer, thereby avoiding catastrophic accidents. Similarly, external short circuit scenarios can be encountered due to control electronics or physical wiring failure. Other misuse scenarios could be possible, which could lead to heating and also to thermal runaways, are scenarios which we'll talk about later on. So you've seen the reasons why it is important to perform a battery analysis, irrespective of whether you are battery manufacturers or battery users. Now, the next question is, of course, how do you perform these analyses? I'm not going to talk about this in too much detail, but in COMSOL, we provide you with the entire range of approaches depending on the kind of approach that you would like to choose for battery modeling. One such approach is the single particle approach, which gives you an electrochemical based approach without the need to solve a very complex model. So it's a quick, fast analysis that you can do, yet you do an electrochemical analysis. And of course, this is valid only for low to medium current discharge rate scenarios. So depending on the kind of analysis that you want to perform, you can choose to do this analysis. This and all the other analyses are hardwired into COMSOL, as you will see later. So all you have to do is choose an approach and then solve it using COMSOL. Then for those of you who do not want to do an electrochemical approach, we have options where you can use a lumped model or do a circuit level analysis. And here you don't need to know any electrochemical information or at the cell level, but you can perform this black box approach based on experimental data that you may have available at your end. You can also do a fully detailed heterogeneous 3D electrochemical approach, and this will give you very accurate results. Of course, this may be a more complex analysis, and it may take you more time to do this. But the point of sharing this with you is that different kinds of analyses for battery simulation can be performed using COMSOL. Apart from the electrochemical part, you can also do thermal modeling in COMSOL. So once you have solved the electrochemical problem, you can also couple it with heat transfer and CFD. And doing this, you can not only capture battery performance, but you can also find out the hot spots, the startup dynamics from cold, and you can also evaluate worst case scenarios where you find out if there is thermal runaway and the catastrophic failures that this leads to. Like I said, we have built-in tools where COMSOL automatically or in the backend couples the electrochemical problem with the thermal problem, and you can also couple this with the CFD analysis in COMSOL. So that's something that I would like to share with you now. An example of how you can build these problems in COMSOL. So as a demo, we will look at how to set up a problem where an air-cooled cylindrical lithium-ion battery is analyzed using COMSOL. We'll simulate the 3D geometry that you see on the right-hand side here, where you have a separator, electrolytes, and electrodes. And we'll start with an electrochemical problem and follow it up with heat transfer and a CFD problem. So having said that, let me exit the software and let me go to our software. So I hope all of you can now see the COMSOL user interface. If not, please let me know. So this is the COMSOL user interface. And what you can do is you can start by selecting the spatial dimension. So you can go from 0D all the way up to 3D. I'm going to choose a 3D spatial dimension here. And then you can start choosing the physics that you are interested in. So you can see I can just go to the battery interfaces, and we have different options here where, as I said earlier, depending on the simulation strategy that you have, you can choose the lithium-ion battery interface or the single particle interface or the lumped or the equivalent circuit option. So you can add this to your model Similarly, I can also go to fluid flow, and I can add, let us say, non-isothermal flow. So I'll go here and choose laminar flow. I could also choose turbulent flow if I wanted to. And once I do this, you can see that in the added physics interfaces, COMSOL shows you the different physics that are now going to be coupled and solved simultaneously. So you can see these physics here, and these will be solved for simultaneously unless you choose to do so otherwise. You can also choose what kind of analysis you want to do. So you can do a stationary analysis, a time-dependent analysis, where it is relevant, for instance, for acoustics or electromagnetics problems. You can also do a time harmonic analysis, if you want to be in the frequency domain. And then when I click on done, I get to the COMSOL user interface, which you can see now. And in the COMSOL user interface, you can now import your geometries, or you can create your geometries in COMSOL. We have tools where you can create your own geometries, and then you can start setting up the problem. So if you can see the model tree on the left hand side, and if I right click here, you can see I can choose different separators, different porous electrode domains. Before I do that, we also have a material library. So if I go to the material library, you see that we have a special material library for batteries, for both electrodes as well as electrolytes. So I can choose my own electrode and electrolyte materials. I can add them to my models. Not only can you add them to the models, but if you click on properties here, we also give you the reference of where we have taken these properties from. So everything in COMSOL is transparent, nothing is hidden from the user. We tell you exactly where everything has come from, and you can now start setting up your problems. Even here, we show you the equations you're solving. So as you can see, you don't have to modify any equations in COMSOL, but we always show you what you're solving, whether it is for the battery physics or for the heat transfer problem or the flow problem. We always show you all the equations, and you can modify them if you want to within the COMSOL graphical user interface without the need to do any scripting. At this point, let me just open a solved model that I have. For the same problem. So, like I said, you start by importing the geometry in COMSOL. In this case, for the problem that we are going to solve now, what we have done is we have solved the electrochemistry problem on a 1D geometry, and the CFD and the heat transfer problem on a 3D geometry. But once again, everything is contained in a single graphical user interface, and COMSOL automatically couples between the dimensions as well. So as you can see, for the 1D electrochemistry problem, we have selected both the electrode and the electrolyte materials. We have then defined the two different porous electrodes, the cathode and the anode, and the separator between them. And then all we have done is given the input or the output current density. So the rate at which we are extracting current when we are discharging the battery, or we are putting in current if we are charging the battery. So that has been specified here. We also have a number of different parameters here to define the electrodes, the electrolyte, as well as the dimensions of the battery. So you can see all of them over here. And you can also see the flow parameters like the inlet velocity over here, right? For the flow problem, similarly, we have defined an inlet velocity over here, as you can see, an outlet velocity on the other side, and an open boundary condition where you have a pressure velocity on this side. And then for the thermal problem, we have made sure that we have a heat source which is automatically coming from the electrochemistry problem. So this is again predefined and not something that you have to worry about. And we have specified an inlet temperature for the entire battery system. Now, once you do that, you can solve this entire problem simultaneously. In this problem, I've already solved the problem. So once the problem is solved, you can then analyze the results. So you can see the load cycle, for instance, the temperature as a function of time, and also the flow, the velocities and the temperature within the cell. So the entire problem can then be analyzed in COMSOL. So this is how you set up a complex multiphysics problem in COMSOL. Now, of course, it requires a certain level of skill to set up these complex problems. You also need access to a COMSOL license to use this problem. I mean, to analyze the data that comes out of this problem. And therefore, to make it easier for designers to have access to these kinds of problems, what we have done is we have also come up with an additional tool called the application builder, which lets our users build their own customized applications within COMSOL. And once they have built these applications, they can then share these applications with their users without the need to have a COMSOL license. So very quickly, I'll show you how you can build an application. Right here, you have an application builder. And if you click on it, you come to a new interface here where you can now start creating your own custom user interfaces. So you can see the different parameters that I had specified are all available here. So I can start choosing which parameters I would like my user to have access to. So maybe I let them change the battery height, the initial velocity, and perhaps the initial temperature. And then I also let them access maybe the cell geometry, as well as maybe the load cycle curves. And I also let them plot the geometry and maybe compute the results. So this is how my customized user interface is going to look now. So if I click on OK, I can now go to I go to the model editor, where I can start modifying my user interface. So I can start changing how my user interface looks. Within the user interface, I can start adding more complexity to my customized user interface. So I can add more input fields, more data displays. I can add drop-down boxes where I can let my users change the materials they are working with. The possibilities are endless. If I click on this test application, you can also see how this application would look. So this is just a quick application that we built in less than a minute. Yes, I'll have to make sure it works in GoToWebinar. So give me a minute. All right. So you can see this is how the application looks. And like I said earlier, to use this application, you don't need a full license of COMSOL. So in this application, my user could perhaps quickly change the battery height, see how it would change. And then if they clicked on this compute button, they would get a completely new result for the modified battery system that they have. Now, using this tool, the application builder, you can build applications which are quite complex, and you can share them with users who don't have access to complex finite element softwares, or who don't have access to license of these softwares, or don't know how to use these softwares. So this is an example of a battery app that we've built here, where as a designer, all you have to do is specify the pack configuration, the number of cells that you have in your battery pack, the operational input. So maybe you have performed some experiments at different temperatures. You can just upload that data, upload the load cycle for which you want to perform the analysis. And once you've done this, without the need to specify any electrochemical parameters, without the need to have set up a problem in the COMSOL software, you can then find out the temperature profile within the entire battery pack, and you can also find out the charge and the discharge curves. So these apps, like I said, can be deployed to designers who have so far had no access to simulation softwares. Now, I've shown you an example of this app for battery simulation. But of course, these apps are not limited only to electrochemical analysis. You can use this for any engineering applications. This is an example from Mahindra, where they have deployed these apps to their design team, and they use them for, in this case, better designing a chassis. So the only parameters that the designers can control here is the number of members that are available in the chassis or the cross section of these members. And based on the choices they make, they get the output of bending and torsional stiffness, and therefore they can see whether it meets design specifications or not. Now, like I said earlier, to run these apps, you don't need the COMSOL software. You can run this using the COMSOL server, where you can host these apps on a central server, and they can be accessed via the web or even via Android clients. We have an app in Google Play Store, and like I said, they can be accessed for free. Or you can also, using the COMSOL compiler, create executables from your COMSOL applications. And then these executable files can be distributed to anybody, and they can operate them for free. In the background, of course, they will be solving the complete complex finite element model, but all they will see is the inputs that are relevant to them and the outputs that are relevant to them. And like I said, these are executable files, so you can just access them for free. So with that, I will conclude this session, and I will hand it back to Ria for the questions. Thank you, everyone.
Thank you, Mr. Vineet, for the insightful presentation and the demo. We now move forward with the question and answer round. So one of our attendees says, in our existing setup for EV, we do not design the batteries and so cannot customize them. We produce batteries from a manufacturer and then need to design packs and modules as per our requirement. We therefore do not have any details about electrode or electrolyte, etc. So he asked, how can COMSOL help us with this case?
Yes, this is a very interesting question. I also touched upon this earlier, but it's important to emphasize. First of all, I understand what the question seeker is talking about, because as a battery user, you often do not have access to material properties. The battery manufacturer may not share this information with you. That's a legitimate concern, and therefore, as a first step, one option is to perform the lumped analysis that I talked about. So when you perform lumped analysis, you don't need any electrochemical data. You can just perform experimentation, and based on the experimentation that you've performed, set up a very reliable model. Experimentation, though, is very important in this case, and you will need to perform extensive experimentation to get some good results. But of course, like I said, if you want to capture accurately features such as capacity fade or SEI layer formation, which will affect battery performance over a period of time, it is also important in due time that you get the electrochemical properties and then perform the full electrochemical analysis. Even if the battery manufacturer does not share this information with you, it is possible to do parameter estimation using experimentation and get the electrochemical properties. As a matter of fact, we have tools in COMSOL which can help you do this as well. So yeah, that's the answer to that question.
Sure. Moving forward, the next question we have is, can we simulate spiral or hypoid gear noise due to electric motor installed at rear drive axle of truck?
Yes, of course. You can capture noise generated by electric motors. Because of the eccentricity, you can have vibration. And I think that's another example that I had shared. If the questioner is interested, I can share these examples with them. But yes, you can couple electromagnetics and structural mechanics and do these kinds of problems in COMSOL. Yeah.
Sure. The next question we have, how does COMSOL help in optimizing the design of PM motors to improve efficiency?
Yeah, so again, with permanent magnet motors, you can one way to do it is like I said, optimizing the laminations around the core. And like I said, we have this functionality of layered shells where you can perform this very efficiently because these laminations are thin. So if you start modeling them as 3D domains, you get a very expensive model in terms of the time taken to solve. But using the layered shell functionality, you can model this as a shell and you can change the material properties in the out of plane direction and therefore still get accurate results. So you can do a coupled structural, electrical and thermal analysis and thereby optimize these PM motors, for instance.
Sure. So another attendee of ours asked, when we discuss about motor electromag analysis, how accurate the results are.
That's a good question. The question is, how accurate are the results? When we design our interfaces, we always make sure that we validate the features that we have developed with some existing literature, and that is shared as part of the software. So we share the validation results that we've used to validate our interfaces. But apart from that, when our users start building their own models, they introduce their own boundary conditions, operating conditions, and of course, errors in geometry, and that could affect the fidelity of their model. The mesh that they create can also affect the fidelity, and therefore, whenever you create your model, it is important that you validate it with existing experiments. I shared a lot of case studies earlier, some from, for instance, from Fiat and the Battery Research Institute in China. In all of these cases, they have also compared their models with experiments and found very good correlation. Once again, for those of you who are interested in looking at experimental comparison of COMSOL results, we have a lot of white papers available on our website. So you are most welcome to visit our website and look at these white papers.
Sure, sir. The another question we have is, how does COMSOL help in design standardization?
In design standardization, so this is something, we don't have any predefined tools for design standardization, but using COMSOL, you can indeed come up with a process which can help you to design standardization. There's no built-in tool though.
Sure. So the another question we have is, what are the requirements or data inputs for the COMSOL software for cell analysis?
Yes. So the question was, what are the inputs required for cell level analysis? I'm assuming these are battery cells. Again, like I mentioned earlier, it depends on what approach you take. So if you say you do not want to do an electrochemical analysis, then all you will need is some experimental data for your drive cycle. Once you've input that data into COMSOL, it will automatically set up a model for your cell. And then you can perform a battery analysis. You can just, load in the drive cycle, the desired drive cycle that you want. I think I shared an app which did exactly that. And you can see how the voltage and SOC changes as a function of time. On the other hand, if you want to perform an electrochemical analysis, then you will need the electrochemical properties of both the electrode and the electrolyte. Now, like I said earlier, we have a built-in material library of electrode and electrolyte properties. But if you are using something different from what is available there, then you will need those properties from your manufacturer or from experiments at your end. So it depends on what kind of analysis you want to perform, the inputs that are required from you.
Sure, sir. Following the questions, we have another question. One of our attendees asks, in the event of a crash, what can prevent both rescuers and passengers from being electrocuted?
Okay. I mean, of course, this is a very serious risk. Um, though, I think we have not heard of this happening yet, but it's important to capture this, or it's important to make sure that we account for this and don't allow this from happening. And again, simulation will help with this. Simulating to make sure that your battery is well insulated in a accident scenario would help. More than this, though, I think a bigger risk is thermal runaway, and we've already seen thermal runaway, accidents causing thermal runaway happening, and that is something that has to be, you have to design for that. So using the simulation tools that are available in COMSOL, you can do both, of course, but I think that the pressing problem is accounting for thermal runaway. And good design will ensure that you minimize thermal runaway even in an accident scenario.
Sure. Coming up is the last question we have. Attendees ask how to safeguard infotainment devices for, say, personal tabs for music and navigation from hot conditions when the vehicle is in open parking.
I see. Well, that's an interesting question. I think that's something that I did not touch upon, but that's another aspect of simulation which COMSOL does perform as well. So if you want to design touch screens, for instance, a lot of automotive users have both automotive as well as cellular phone users of ours have used COMSOL to design touch screens. And because it's a multiphysics software, you can couple the electrical uh, and the electronic analysis with heat transfer and see how high temperatures affect electronic performance, and devise a cooling strategy based on the layout of your device. So once again, that is possible in COMSOL, even though I didn't touch upon it today. And I would again like to say that if you're interested in these aspects, please do contact us and we can share the relevant white papers with you.
Sure. So thank you so much for answering all the questions, and thank you so much for being here with us for this webinar. I'm equally grateful for all the attendees for being here with us. Thank you and have a great day ahead.
All right. Thanks a lot. It was nice interacting with you. Thank you.